So in Calc 1, we talked about functions of one variable and integrating a function like this over an interval in the real line. And so the basic idea was the function had a domain in R, we picked some interval AB, we took this interval, chopped it up into a number of skinny pieces. Each one of these skinny pieces had a tiny little length of delta x. And so what we did was we added up each of those tiny widths times the function evaluated at a sample point on the inside. And then by taking the limit, we built an integral. Then for a function of two variables, we did the same thing. What we did is we started off with the domain, and inside that domain we would have some kind of a region, say R. We would take that region, if we needed to sort of enlarge it with a rectangle, slice that rectangle up into small pieces, where each one of these pieces had the same height, delta y, and the same width at delta x. And what we do is we would add up the width times the height times a function value at some specific point. And then when we took the limit of these, then we called this an integral. We called it a double integral over the region R because we were essentially summing two different kinds of things. And if we sort of thought about what delta x, delta y was measuring, it was measuring a tiny little segment of area, the area of this one little square. And so we used dA to indicate that we were summing up over small chunks of area. So what about a function of three variables? Is it possible to do something similar? Well, keeping with the spirit of what we did here, what would we integrate over? Well, it would have to be some kind of a three-dimensional solid in R3. What would be our integration concept? Well, the first thing that we would do is we could take this region and we could enclose it inside of a block, which we would then subdivide into a number of even pieces, say a number of skinny pieces in the x direction, followed by a number of skinny pieces in the y direction, followed by a number of skinny pieces in the z direction. What we could then do is we would sum up for each one of these little blocks the length times the width times the height of these guys times f evaluated at some point x, y, z inside that little block. And what we would do is we would take the limit of these things and we would build an integral out of it. Well, the symbol should be a triple integral, since we're talking about three-dimensional things, over whatever this solid is, and a traditional name for this is D, for a domain. What about the D symbol? Well, in this case, we're measuring little length times width times y's. In other words, we're multiplying by the volume of one of these little tiny blocks right here. And so the traditional choice of letter is dV for summing up of volumes. And so without going into all of the details, this is going to be our effective definition of what a triple integral is. A triple integral is going to be a special limit of sums right here. It's going to be the sum of f evaluated at a point xi, yi, zi times delta x, delta y, delta z, where the sum is taken over those points xi, yi, zi inside the point D, and the limit is taken as the number of delta x, delta y, and delta z slices tends to infinity. We can make the symbols more precise, but we have a fairly decent idea of what this is right here. Because we're following the same procedure we used for double integrals and the same procedure we used for single variable integrals, it's not too surprising that a lot of the same characteristics or the same theorems hold for triple integrals as they do for double integrals. For example, the triple integral of a constant times a function over some domain is equal to the constant times the triple integral of that function over the domain. Or, the triple integral of a sum of two functions over a domain is the sum of the two triple integrals over the same domain. Or even, the triple integral of a function over a region who can be split into two pieces d1 and d2 is simply the sum of the two triple integrals over those two separate pieces. Pretty much the only thing that doesn't come along with it is the basic bit of geometric intuition. Specifically, that the triple integral of a function is the net signed four-dimensional hypervolume of a hypersolid formed between the xyz space and the hypersurface W equals xyz. The fact that we have all of this four-dimensional hyper stuff is an indication that we've lost the geometric intuition about what these constructs are, but we can still work with them. For example, one last useful piece of information that can be extended from the one variable or the two variable case is the idea of Fubini's theorem. Let's consider the simplest possible domain that we could integrate over in three-dimensional space. Some rectangular brick. If we were to look straight down on the brick, its shadow in the xy plane would be some rectangle, say one that goes between A and B in the x direction and C and D in the y direction. If we further mark off that its height stays between U and V on the z-axis, then Fubini's theorem would say that the integral of the function f of x, y, z, or over the prism AB cross CD cross UV, would be equal to any number of iterated integrals. For example, we could take the function f of x, y, z and integrate it first with respect to x between A and B, and then integrate this with respect to y between C and D, and then integrate this with respect to z between U and V. Or we could take the function f of x, y, z, integrate it first with respect to z from U to V, then integrate that with respect to x from A to B, and then integrate that with respect to y from C to D. Or we could go and integrate the function f of x, y, z with respect to y first from C to D, and then with respect to z from U to V, and then with respect to x from A to B. Or in fact, any of the three other ways we could order dx, dy, and dz. All of these things would match up on the proviso that f is continuous. Compute the triple integral over the domain D of the function x plus yz dv, where D is the rectangle 0, 1 by 0, 2 by 1, 2. So let's just go and use Fubini's theorem on this. What we're going to do is we're going to turn this into an iterated integral, where we're going to integrate with respect to each one of the variables in a specific order. Now Fubini's theorem says it doesn't matter what order we do, so if we were to integrate them in the order x, y, z, then we would integrate x from 0 to 1, we would integrate y from 0 to 2, and we would integrate z from 1 to 2. And so let's work out this iterated integral, starting with the inside first. So if we were to go and integrate x plus yz with respect to x first, we would get 1/2 x squared plus yzx, which will then evaluate from x equals 0 to x equals 1. So when we plug in 1, we're going to get 1/2 plus yz. When we plug in 0, we're going to get 0 plus 0. And so that will give us 1/2 plus yz. And so we have the first of our iterated integrals. So now we're going to have to go and integrate from 1 to 2, the integral from 0 to 2 of the function 1/2 plus yz dy dz. So now let's focus on this piece, whose work will extend down to here. If we integrate 1/2 plus yz with respect to y, we're going to get 1/2 y plus 1/2 y squared z, evaluated from y equals 0 to y equals 2. If we plug in y equals 2, we're going to get 1/2 times 2 plus 1/2 times 2 squared times z. If we plug in 0, we're going to get 0 plus 0, and so that will become 1 plus 2z. And so now we have the inside iterated integral. And so now we need only integrate from 1 to 2 the function 1 plus 2z dz. And we'll just carry that work down here. So if we integrate 1 plus 2z with respect to z, we're going to get z plus z squared, which will then evaluate from z equals 1 to z equals 2. So when we plug in 2, we're going to get 2 plus 2 squared. When we plug in 1, we're going to get 1 plus 1. So that gives us a grand total of 6 minus 2, or 4. And so the triple integral is equal to 4. Now, just to sort of highlight Fubini's theorem, let's redo the problem, but taking the variables in a different order. Say z first, then x, then y. So when we integrate this with respect to z, we're going to have to go from 1 to 2. When we next integrate this with respect to x, we'll have to go from 0 to 1. and then finally for y between 0 and 2. So we'll start off with the first iterated integral. We're going to integrate x plus yz, this time with respect to z. So that'll get us xz plus 1/2 yz squared, which we can then evaluate from z equals 1 to z equals 2. When we plug in z equals 2, we're going to get 2x plus 1/2 times y times 2 squared. When we plug in 1, we're going to get 1x plus 1/2 times y times 1 squared. And so that's going to give us a grand total of 2x plus 2y minus x minus 1/2 y, or x minus or positive 3/2 y, as our first iterated integral. So we'll take this and plug it inside, and now we have to do the iterated integral from 0 to 2 of the integral from 0 to 1 of the inside function x plus 3/2 y dx dy. So now let's focus on the next iterated integral, which we'll do right here. So we're going to integrate x plus 3/2 y with respect to x. That'll get us 1/2 x squared plus 3/2 yx, which we can then evaluate from x equals 0 to x equals 1. So plugging in x equals 1 will get us 1/2 plus 3/2 y times 1. Plugging in 0 will just get us 0 plus 0. And so that becomes 1/2 plus 3/2 y, which we can now plug into here. And we'll have the final iterated integral from 0 to 2 of 1/2 plus 3/2 y dy. And so this last iterated integral will just carry out down here. So we're going to integrate the function 1/2 plus 3/2 y with respect to y. That'll give us 1/2 y plus 3/4 y squared, evaluated from y equals 0 to y equals 2. We plug in 2, we're going to get 1/2 times 2 plus 3/4 times 2 squared, which is 4. When we plug in 0, we're going to get 0 plus 0. So that'll give us a grand total of 1 plus 3, which is 4, which agrees with our previous calculation. So in the simple case of a rectangle, Fubini's theorem is fairly effective, but what about more complicated regions? Well, in the two-dimensional case, there were two different Fubini's theorems, one for regions who were horizontally simple, and one for regions who were vertically simple. Well, there's going to be three different versions of Fubini's theorem for a function of three variables. So the first case we want to look at is the case when z is sometimes called a z-simple domain. So what this means is you have a domain where every line parallel to z inside this domain, if we were to somehow draw all of them, they would have the exact same surface defining the top edge of their shape and the exact same surface defining their bottom edge. So let's say that this top surface is of the form z equals top of xy, and the bottom surface is of the form z equals bottom of xy. And so this surface simply consists of all of the points in between these two surfaces, like this shape right here. Now if we were to look straight down the z-axis at where all of these points sort of hit the xy plane, we'd see some sort of a region down here in the xy plane. And so this whole surface would look like a shape suspended above that particular region right here. I'll call this region xy, since this region would be in the xy plane. So that means that this shape right here could be described by saying that the z values always stay below the top surface, z of t, z equals t of xy, and above the bottom surface, z equals b of xy. And the points xy stay in the region R in the plane. This is what we mean by a z-simple domain. Well, Fubini's theorem says that in the case of a z-simple domain, then the iterated integral, then the triple integral over this domain of the function f of x, y, z, dv, can be expressed as an iterated integral. First, we're going to integrate the function f of x, y, z with respect to the variable z from the bottom surface to the top surface. Notice that when we're done with integrating this, this will be an expression in x and y. And so we can then doubly integrate that expression over the region R. So this allows me to take a triple integral and express it as an iterated integral of a one variable and a two variable integral. Now, what are some of the other domains for which this would apply? Well, you could imagine, for example, Well, what an x-simple domain is, well, this would be a domain where if we take every single line in it which runs parallel to x, they would all have the same surface on the low end, say some surface like this. Say the surface takes the form x equals L of yz for the left-hand side, and all of the right-hand points would be on some other surface over here, which we could maybe call x equals R of yz. And so the surface would consist of all of the points who are wedged in between these two surfaces here. Say something like this. If we were to look straight down the x-axis and look at sort of the shadow that this shape casts in the yz plane, its shadow, if you will, then we would have a region, which we'll call R of yz, in the ry plane. And so a region who is x-simple would take the form x stays between a left-hand surface, x equals L of yz, and a right-hand surface, x equals R of yz, while the yz values themselves stay inside some region R of yz. Oops, I just noticed I forgot the xy up here. So a region like this would be x-simple, and then Fubini's theorem would say that in such a case, the double or triple integral, over the region D of f of x, y, z, dv could be expressed as an iterated integral. We would first integrate the function f of x, y, z with respect to the variable x from the left-hand surface, L of yz, to the right-hand surface, R of yz. Notice that this kind of an integral is going to leave a formula with y's and z's in it. And so we'll take that formula and then we'll double integrate it over the region ryz with respect to a. It will be a double integral. Oh, I forgot the xy up here. And so this would be Fubini's theorem again. And so there's also a corresponding statement if D is y-simple. The easiest way to try working with this is simply to put it into practice. So let's give it a shot on this example. Compute the triple integral of z dv over d if d is the region bounded by the xy plane, the parabolic cylinder y equals x squared, and the plane y plus z equals 1. So the plane D is shown right here. So let's try to get some bearings on what these pieces are right here. The xy plane, well, that's just the bottom shape, the bottom part of this wedge shape. Remember that the xy plane is nothing more than the plane z equals 0. Then we also have this plane y plus z equals 1, which must represent this part right here, the flat plane that sort of defines this top edge of the shape right there. And that's kind of consistent. If we look at how this crosses the yz plane, then we would see a line like this. And in the yz plane, y plus z equals 1 is the same thing as saying that z is equal to negative y plus 1. So we'd expect to see in the yz plane a line of slope minus 1. So that's fairly consistent. Finally, the parabolic cylinder y equals x squared. Well, I know that in the plane y equals x squared would be this parabola right here. But since this is a surface, it means that every single one of its z traces would also be y equals x squared. And so this surface would describe a giant cylinder going up like this. So I have a cylinder that goes forever like this. We've sliced it at the very, very bottom with the xy plane, and then we've sliced a diagonal plane running through it. And so that shape, rounded on the sides from the cylinder, flat across the top from the plane y plus z equals 1, and flat across the bottom from the plane z equals 0, is exactly the shape we see. So can we describe this object as a simple domain, and then we could use Fubini's theorem? Well, maybe the most obvious way to describe it as a simple domain is to describe it as z-simple. Every time I draw a vertical line in this domain, one surface defines the top edge, namely this plane right here, and another plane defines the bottom edge. So this certainly looks like it would be z-simple. What would it look like if we stared straight down? Well, if we stared straight down, we would see just this shape right here. If I were to draw that in the xy plane, then what we'd see is we would see the parabola y equals x squared, like this. And so this certainly seems like this would be a region that we could describe as being vertically simple. We could describe this domain as the set of all points where z stays above the plane z equals 0, which is the xy plane, but below this top plane. Now that's the plane y plus z equals 1, or if we solve it for z, z is equal to 1 minus y. So there's the top part. And now we know that x and y have to stay within this parabolic shape right here. And so we could describe the domain D loosely like this. And then Fubini's theorem would say that the triple integral over the region D is going to be the iterated integral, where we'll take the function z and we'll integrate it with respect to z from the bottom surface z equals 0 to the top surface z equals 1 minus y. And then we'll take that and we'll double integrate that over the region R as a double integral. So let's focus on this inside region right now. If we take the integral of z with respect to z, that will become 1/2 z squared, which we can then evaluate from z equals 0 to z equals 1 minus y. So that will become 1/2 1 minus y squared minus 1/2 0 squared. So if we ignore that and expand out this piece, we're going to get 1/2 of 1 minus 2y plus y squared, or 1/2 minus y plus 1/2 y squared. And so if we plug this into here, we're now forced to evaluate the double integral of 1/2 minus y minus 1/2 y squared dA, where R is this parabolic region right here. So now we've got a double integral. Well, the easiest way to attack a double integral would be to describe the region R as being either vertically or horizontally simple. In this case, the region R is actually quite easily seen to be vertically simple. It has the same top curve, this horizontal line right here, and the same bottom curve right down here. How can we figure out what these things are? Well, let's go and take the picture above as context. This top line in the 2D picture is this line right here. Notice that that's the line where the top surface, the equation the equation y plus z equals 1 intersects the plane z equals 0. So where do those 2 points meet? Well, let's find out. If we were to go and take the top equation, which is z equals 1 plus or minus y, the bottom equation is z equals 0. So these 2 equations meet when the z values match. So 1 minus y is equal to 0, or y is equal to 1. So this top curve right here has to be the line y equals 1. The bottom curve is y equals x squared. Where are these 2 endpoints? If the y value is equal to 1, then the x values have to be plus or minus 1. So this is the point positive 1, 1, and this is the point minus 1, 1. And so we can describe this region R as follows. R is the region where the y values stay above the parabola y equals x squared, but below the line y equals 1, and the x values go from the farmost left x value of negative 1 to the farmost right value of positive 1. This integral can now be attacked by an iterated integral. We can integrate it first with respect to y, since it's vertically simple, so we'll take 1/2 minus y minus 1/2 y squared and integrate it with respect to y from y equals x squared to y equals 1, and then we'll integrate this with respect to x going from minus 1 to positive 1. So let's make some scratch work and continue with this iterated integral up at the top, up here. Let's go and integrate 1/2 minus y plus 1/2 y squared. Oh, I just noticed these should have been pluses the whole way through. I made a copy error right there. With respect to y. So if we continue with the work, we'll get 1/2 of y minus 1/2 y squared plus 1/6 y cubed, which we can evaluate from y going from x squared to y equals 1. So when we plug in y equals 1, we're going to get 1/2 minus 1/2 plus 1/6. When we plug in x squared, we're going to get 1/2 x squared minus 1/2 x squared squared, or x to the 4th, plus 1/6 x to the x squared cubed, or x to the 6th. And so that will get us a grand total of 1/6 minus 1/2 x squared minus negative 1/2 x to the 4th minus 1/6 x to the 6th. And then finally, we can integrate this expression with respect to x from -1 to 1. So we'll get 1/6 x minus 1/6 x cubed plus 1/10 x to the 5th minus 1/42 x to the 7th, which we can then evaluate from -1 to 1. So if we plug in 1, we're going to get 1/6 minus 1/6 plus 1/10 minus 1/42. If we plug in -1, we'll get minus 1/6 minus minus 1/6 minus 1/10 and minus minus 1/42. So the 1/6 will cancel in both of these places, and what we'll get is 1/10 minus 1/42 minus minus 1/10 minus 1/42, or a grand total of 16 1/105ths. Now there's a couple of observations I'd like to make about this before we go on to another problem. The first thing is that we could combine our description of R and D into one string of inequalities by taking this part and plugging it into there. In this case, we would get that D would take the form Z stays between 0 and 1 minus y, but y stays between x squared and 1, and x stays between -1 and 1. So in this case, the z value has inequalities that involve x's and y's, the y value has inequalities that involve x only, and the x value has inequalities that involve purely numbers. Moreover, Fubini's theorem would then say for something like this, that the integral involves taking the function f of x, y, z, integrating it first with respect to z from z equals 0 to z equals 1 minus y, and then integrating this expression with respect to x's and y's. But Fubini's theorem on that would say we would have to integrate this with respect to y first, because it was vertically simple, y going from x squared to y going to 1, and then we would integrate that finally with respect to x going from -1 to 1. So in some sense, this right here is the complete Fubini description of an integral of something which is z simple over a vertically simple region. The other observation I want to make about this problem is that we don't have to view it as a z simple region. Notice instead that if we were to draw lines who were parallel to the x-axis, then every parallel line would always have on the right-hand side this surface, the right-hand side of that parabolic cylinder, as its left surface, and the right-hand side the left-hand side would be this part of the surface. If you can't quite see that, imagine for a second looking straight down, like we did before. From a top-down view, we would see a shape. And right now I'm drawing the axes a little bit skewed. We would see this big blue shape right here. And so every horizontal line has this portion of the cylinder forming the right side of it, and this portion of the cylinder forming the left side of it. Since this equation, the equation that defines the cylinder, is y equals x squared, if we solve that for x, since I'm taking lines parallel to the x-axis, we would get x is equal to plus or minus the square root of y. Well, evidently, this piece right here, on the positive x direction, must be the bit x equals positive the square root of y, whereas this piece must be x equals negative the square root of y. So we could equally describe this domain by saying that its x values always stay to the right of the curve negative y, but always stay to the left of the curve positive square root of y. And then the yz's are going to stay in their own particular region in the yz plane. Now, what would that yz region look like? Well, imagine instead that you were to stand on the xy plane and look straight down the x-axis. What shape would we see? Well, what we'd see is we'd see something like this. A triangle. The bottom edge of this triangle would be the curve z equals 0. The top edge of this triangle we've already seen is z plus y equals 1. So such a shape in the YZ plane is again vertically simple, where now Z is playing the role of the vertical component. So the vertical pieces always stay below the surface Z equals 1 minus Y, but they stay above the line Z equals 0. The Y values stay, well, the far leftmost Y value is 0, and the far rightmost Y value, this point right here, we've already seen as Y equals 1. So we could describe this region R by saying that the Z values always stay below the curve 1 minus Y, but above the curve 0. And the Y values always stay above 0, but below 1. And so this description right here gives us a description of the domain as an X-simple domain, which we can then apply Fubini's theorem on. Fubini's theorem would say that the triple integral over this domain of the function would be the function z evaluated first with respect to x, with x going between the negative, the square root of y, and the positive square root of y. And then we would integrate that with respect to z next, where z goes between 0 and 1 minus y. And then finally we would integrate with respect to y, between y going from 0 to 1. And so this would be a different iterated integral that Fubini's theorem says should give us the same value. So let's test it out. Starting on the inside, let's go and integrate z with respect to x. That'll get us zx evaluated from x equals negative the square root of y to x equals positive the square root of y. So that gets us z times the square root of y minus negative z times the square root of y, or 2y to the 1/2 power z. So now we'll plug that into the inside, and we'll focus on the next iterated integral. The integral from z equals 0 to z equals 1 minus y of 2y to the 1/2 z dz. So if we integrate this bit, which we'll do down here, if we integrate 2y to the 1/2 power times z with respect to z, we're going to get y to the 1/2 power times z squared evaluated from z equals 0 to z equals 1 minus y. So that will get us y to the 1/2 power times 1 minus y squared minus y to the 1/2 power times 0. So that cancels, and we're left with y to the 1/2 power times 1 minus y squared, which expands to 1 minus 2y plus y squared. And if we distribute through, y to the 1/2 power minus 2 times y to the 3/2 power plus y to the 5/2 power. And so that's the inside integral of this expression in green. And so now we need to integrate the function y to the 1/2 minus 2 times y to the 3/2 plus y to the 5/2 dy from y going from 0 to 1. And so one more round of the fundamental theorem would say that this is y to the 3/2 power times 2/3 minus 2 times y to the 5/2 power times 2/5 plus y to the 7/2 power times 2/7 evaluated from 0 to 1. If we plug in 1, we're going to get 2/3 minus 4/5 plus 2/7. If we plug in 0, we're just going to get a bunch of zeros. And so our final answer will be 2/3 minus 4/5 plus 2/7, which, if we put on the common denominator, is 16 1/05, just like it was last time. Set up the iterated integrals for the triple integral of the function f of x, y, z dv over w in the orders integrating dx, dy, dz and integrating dy, dx, dz if w is the tetrahedron with corners at 0, 0, 0, 2, 0, 0, 0, 3, 0, and 0, 0, 5. So notice that this problem is all about simply setting up iterated integrals, but not actually integrating those. So this is really a problem about Fubini's theorem and trying to figure out how to express a particular region in terms of dx, dy, dz, or dy, dx, dz. So as a starting point, let's first try to draw what this shape is. We have some idea of what we're talking about here. So here's the x, y, z axes. So it's a tetrahedron, which means it's a four-sided solid, like a four-sided die. It's got a corner here at the origin. It's got a corner here 2 units along the x-axis. A corner here 3 units along the y-axis. and a corner here 5 units along the z-axis. And so we're looking at this four-sided solid right here. Notice that 3 of the 4 faces of this solid are just coordinate planes. For example, the bottom face down here is nothing more than the plane z equals 0, the xy plane. This front face right here is nothing more than the xy plane, which is just y equals 0. Similarly, this back side is the yz plane, which means it's the equation x equals 0. What about this front diagonal face, which is maybe the only interesting one right here? Well, because it's a flat sheet, it must be a plane, and in fact it's the plane who passes through these 3 points right here. And so we could quickly solve for that. What's the plane through the points 2, 0, 0, 0, 3, 0, and 0, 0, 5? Remember, our trick from earlier in the semester is we'll take 2 different vectors who live inside this plane. So, for example, the vectors who connect the top point to each of these. So those 2 vectors would be 2, 0, negative 5, and 0, 3, negative 5, by doing tip minus tail. Their cross product would then provide a normal vector, which we could then use to find the equation of the plane. So if we work through this, we can set up the determinant, expand it, and come up with the vector 15, 10, 6 as being normal to the 2 vectors in the plane, and therefore normal to the plane. And so now that we have a normal vector, the equation of the plane is simply that normal vector times the variable vector equals the normal vector times any one of the points on the plane, for example, the point 2, 0, 0. And so if we expand this out, we get 15x plus 10y plus 6z is equal to 30. We can check that all 3 points satisfy this, and so now we have the final plane. So now let's go about setting up the iterated integrals. To do the iterated integral in the form of dz dx, or dy dx, the first thing we need to do is to describe this region as being simple in the z direction. So that means we need to take lines who run parallel to the z-axis and see if they have a common top and bottom surface. We'll notice that as long as you're inside this region, your top will always be the slanted plane, and the bottom of every vertical line will always be the flat Euclidean plane. So we could describe this region, W, by saying that its z values always stay above the plane z equals 0, but below this blue plane. Let's quickly go and solve this equation for the variable z. We would have 6z is equal to 30 minus 15x minus 10y. And so if we divide everything through by 6, we'll get z is equal to 30 divided by 6, which is 5, minus 15 divided by 6, which is 5 halves x, minus 10 divided by 6, which is 5 thirds y. And so that's the equation of the upper surface. And we know that the z values always stay below this upper surface. Now, we need to somehow describe the x and the y variables. To do that, let's imagine looking straight down the z-axis so that we can only see the shadow in the xy plane. In the xy plane, we would see a triangle shape. One of its corners would be at the origin, its other corner would be here at the point x equals 2, and its other corner would be at the point y equals 3. So, if we wanted to go and describe this next region, this next integral, with respect to y, well then we need to describe this shape as vertically simple, as simple in the y direction. So we take lines who are parallel to the y-axis. Every single one of these lines has the same top curve and the same bottom curve. The bottom curve is the x-axis, the equation y equals 0. The top curve is a line who has a y-intercept of 3, and it has a slope, well let's see, it drops 3 units for every 2 across it goes. So the top is that equation right here. And the y values must stay between them. So the y values have to stay above the curve y equals 0, the x-axis, but below the slanted line y equals 3 minus 3 halves x. And finally, once we've got it described like this, the leftmost x value is x equals 0, the rightmost x value is evidently x equals 2. And so we've described this region W in terms of x's, y's, and z's, where the z variable is described in terms of x's and y's, the y variable is described in terms of x only, and the x variable is described in terms of purely numbers. So armed with this description of W, we can now integrate the function f of x, y, z. First, we'll integrate it with respect to z. So the bottom limit will be z equals 0. The top limit will be z is equal to 5 minus 5 halves x minus 5 thirds y. Next, we'll take this integral and integrate it with respect to y, where y will go from y equals 0 on the bottom to y equals 3 minus 3 halves x on the top. And last but not least, we'll integrate this integral with respect to x, where x will go from 0 to 2. And so this expression right here would represent the iterated integral in the order dz, dy, dx. Now what about the second ordering, dy, dx, dz? Well, let's start fresh. Since we first want to integrate it with respect to dy, we're going to need to describe this region as being simple with respect to the y-axis. So that means we're going to take horizontal lines who are parallel to the y-axis through this region and see whether or not they have the same terminal faces. Notice that the left-hand side of every one of these things must live along this bottom flat sheet, which was the plane y equals 0. The top half of each one of these segments lies on the slanted plane, which if we solve for y, is y equals 30 minus 15x minus 6z over 10, or y is equal to 3 minus 3 halves x minus 3/5 z. So we can start by describing the set W by saying that the y values stay above the plane y equals 0, but below the plane y equals 3 minus 3 halves x minus 3/5 y. Now we can focus on the next iteration. We want to go and describe the remaining portion, the planar region, in terms of x first. So in order to do that, let's go and take a look straight down the y-axis and see what shape we get in the xz plane. We can kind of see that shape right here. I'll just draw another sketch of it right here. In the xz plane, we see a triangle who has a vertex at the origin, one corner at the point x equals 2, and another corner up here at the point z equals 5. Now, since we want to integrate this with respect to x, we need to describe this region as being horizontally simple, because we want to describe it with lines running parallel to the x-axis. Notice that every left-hand side is along the z-axis, which is the line x equals 0. The right-hand side lives along this line right here. Now in the xz space, this line is easy to write down. It's got a z-intercept of 5, and it has a slope of negative, let's see, it drops 5 units for the 2 across it goes. So if we solve this for x, we'll get 5 halves x is equal to 5 minus z. We can multiply both sides by 2/5, and we'll get that x is equal to, by distributing through, 2 minus 2/5 z. So the x values stay between 0 and the curve 2 minus 2/5 z. Finally, the z values. Well, the lowest z value is down here at z equals 0. The highest z value is up here at z equals 5. And so the z values will stay between 0 and 5. And so this becomes our description of the set W. And armed with it, we can now talk about how we would go and integrate the function f of x, y, z with respect to dy, then dx, then dz. To integrate it with respect to y first, we'll go from the curve y equals 0 to the curve y equals 3 minus 3 halves x minus 3/5 z. Then we'll integrate this with respect to x, going from x equals 0 on the bottom to x equals 2 minus 2/5 z on the top. And then finally we'll integrate this expression with respect to z, where z will go from 0 to 5. And so this represents the iterated integral in the order dy, dx, dz. Maybe one of the troubling bits about our work so far is that we don't have any intuition as to what a triple integral is meaning. We can compute them, but we don't have any picture for what it is. However, it turns out that on the proviso that this is a positive function, that f is never negative, there is a nice three-dimensional interpretation I can give for it. So imagine we've got the set W, the region that we're integrating over. Say this region right here. Now, suppose it was made out of a non-uniform material, so a material which is sometimes, say, thicker in some places and thinner in some places. And so at every point inside here, there might be a density. And let's say that this density is given exactly by the function f of x, y, z. So in some places, it might have a higher density. In other places, it might have a lower density. Well, what does the Riemann sum represent here? And the idea of the Riemann sum is we took this shape and we chopped it up into small subdivisions and added them up over and over and over again. So I'm just going to draw a couple of representative subdivisions. So what does this expression f of xi, yi, zi, delta x, delta y, delta z actually mean right here? Well, this part right here is simply the volume of the subdivision. This part right here is the density at a single point. Now, if this particular block was small enough, we could pretty much assume that the density at this one point would pretty much be the density of the entire block. And so this part right here represents approximately the volume of a block times a constant density. This would be the mass of that tiny subdivision. And so if we were to go and add up all of these Riemann sums, then we would be adding up the masses of each one of these tiny subdivisions. And so that would be the total mass. So every Riemann sum is an approximation of the total mass of this three-dimensional object. If we take the limit, well, then the approximation goes away. And so the triple integral of a positive function is simply the mass of the solid W given a varying density given by that function right there. One special case, if the function is identically equal to 1, i.e. the solid has a uniform density, well then the triple integral of 1 dv is just going to be the volume of the solid. And so we have a neat way of expressing volumes and masses of three-dimensional objects. It's worth pointing out, these arguments would have remained the same even in 2 dimensions, with one slight tweak. If we'd had some region in the plane, say this region R right here, and at each point we assigned what's called a planar density, so sort of the density of a small chunk right here, well then the double integral of f of x, y, dA would have been what's called the planar mass of the region W, or the region R, sorry, given the varying density of f of x, y at each point. And the special case of the function 1 would be the planar volume, which is sometimes called the area of the region. And so we've come up with another interpretation of a 2-dimensional double integral as a 2-dimensional representation. Suppose T is the tetrahedron from the previous example, and let's say that it's filled with a fluid that over time begins to settle, so that it's denser at the bottom than it is at the top. If its density is given by the equation rho of xyz equals 5 minus z, find its mass. So remember, we had this tetrahedron from last time right here, and we're saying that it's denser at the bottom than it is at the top. So how would we find its mass? Well, that was just what the previous example stated. We'd simply take the tetrahedron and we'll integrate the function rho of x, y, z over the tetrahedron. Now from last time we worked out 2 different iterated integrals for doing this. So one of those integrated integrals was the following. So let's work on this one. We'll start by doing the inside integral first. So we'll go and we'll integrate the function 5 minus z with respect to y first. So we integrate that with respect to y, we're going to get 5 minus z times y, since this whole expression is a constant, evaluated from 0 to 3 minus 3 halves x minus 3 fifths z. And so that will get us a grand total of 5 minus z times 3 minus 3 halves x minus 3 fifths z, and we plug in y equals 0, we'll get nothing. So this is the new expression we need to integrate. So now, Let's integrate the second iteration. So we're going to go and integrate 5 minus z times 3 minus 3 halves x minus 3/5 z dx. Now notice that this is a constant, so again it will come along for the ride. We're going to go and integrate the inside expression to get 3x minus 3/4 x squared minus 3/5 zx, which we can then evaluate from x equals 0 to x equals 2 minus 2/5 z. So when we plug in the top, we're going to have 5 minus z times 3 times x, which is 2 minus 2/5 z, minus 3/4 times 2 minus 2/5 z squared, minus 3/5 times z times x, which is 2 minus 2/5 z. When we plug in x equals 0, everything will cancel, and so this will become the expression we have to work with. Now if we clean this up, we're going to have 5 minus z times 6 minus 6/5 z minus 3/4 times 4 minus 8/5 z plus 4/25 z squared minus 3/5 times 2, which would be, 6/5 z minus negative 6/25 z squared. If we continue this work up near the top, we would have 5 minus z times 6 minus 6/5 z minus, distributing through, 3 minus negative 6/5 z plus minus 3/25 z squared minus 6/5 z plus 6/25 z squared. Notice that the 6 and the negative 3 cancel to get us 3. Negative 6/5 and positive 6/5 z cancel, leaving us only negative 6/5 z. And then 6/25 z squared, take away 3/25 z squared, would be 3/25 z squared, which we can then multiply by 5 minus z. So if we expand this out, distributing through by the 5, we'll get 15 minus 6z plus 3/5 z squared. Distributing the negative z in, we'll get negative 3z minus negative 6/5 z squared minus 3/25 z cubed. And then if we clean this expression up, we have 15 minus 9z, 9/5 z squared minus 3/25 z cubed. And so that finally can go inside here, and we're left with one final integral to do. Let's get a little bit of free space. So if we integrate 15 minus 9z plus 9/5 z squared minus 3/25 z cubed with respect to z, we'll get 15z minus 9 halves z squared plus 9/5 times 1/3 z cubed minus 3/25 times 1/4 z to the 4th, evaluated from 0 to 5. So when we plug in 5, we'll have 15 times 5 minus 9 halves times 5 squared plus 3/5 times 5 cubed minus 3/100 times 5 to the 4th power, which is 625. And so that gets us a grand total of 1,875, or 18.75 exactly. So the mass of this object would be 18.75 in whatever units we choose to measure it.